Good day and a very warm welcome on behalf of NTI Audio. Today we are talking about the basics of sweep analysis, and we have actually focused on the fundamental aspects of sweep analysis only. So we may already inform you that we will broadcast a second webinar on that topic in the near future. In this follow-up webinar, we will cover more profound, more detailed aspects of sweep analysis. But today we are focusing on the basics. My name is Markus Becker and I'm assisted today by Greg Schmiedle, who is responsible for answering to your questions. The contents that we have prepared for you start with a brief look on the motivation, why to execute sweep analysis and some applications. We will then take a closer look on the most frequently used sweep measurements, sweep types, and parameters. Afterwards, we have prepared a practical presentation for you before we will summarize the key information of this webinar. And at the very end, I will come back to the questions that have popped in and possibly add some comments. I expect that the whole presentation will last approximately half an hour. Why do we have to execute sweep measurements? It is quite obvious that when we want to characterize the performance, the behavior of a device such as a loudspeaker, a microphone, an amplifier, whatever, we should do that over the whole frequency bandwidth in which this product can be operated, rather than just measuring a single frequency. So in other terms, in order to execute a comprehensive analysis of any device, we have to record the behavior over the frequency or the level range. And that is what we do with a sweep. Examples are the measurement of the frequency response or the detection of audible defects, distortions or rub and buzz in a loudspeaker, the measurement of phase or crosstalk and other related analysis, or even generic measurements as, for instance, the power versus the input level or versus the frequency. Well, when we talk about sweep measurements, we should also clarify the wording. So in order to avoid any ambiguity or misunderstanding. First of all, we usually talk about the frequency response as the measurement of the level here on the y-axis versus the frequency. That is typically referred to as the frequency response. The distortion response, of course, on the other side, means that we are measuring now the distortion versus the frequency axis. Then we have, in this example, the measurement of the distortion, again, on the y-axis versus the power, for instance, the output power of an amplifier. Or, as a fourth example, when we talk about linearity, we are measuring the output level of a device, typically of an amplifier, versus the input level to that amplifier. Linearity is typically acquired by means of an amplitude sweep, and I will explain that just in a minute. When we talk about sweep types, we are differentiating two groups. We have the StepSweeps on one side, and we have the GlideSweep on the other side. And the StepSweep here that you see on this slide has 4 subgroups. Let's start with the frequency sweep. The frequency sweep means that we are increasing stepwise the output frequency of our generator. This would be the first one that has been generated, changing over to the second frequency, the third, and so on and so forth. While on the analyzer side, we are measuring the response of our device under test. A similar but a little bit more exotic application would be the table sweep. The table sweep means that we are not only changing the frequency, but also the level. And this in a random order, or random in a user-defined order, which means we can increase or decrease the frequency from step to step according to our preferences. The Amplitude Sweep, as mentioned before, is an application where we have a fixed frequency, and now we are increasing in steps the input level of our device under test, or the output level of the generator. And the fourth step sweep method is the so-called time sweep. The time sweep actually is a kind of a monitoring the device over time, which means we are acquiring measurements in predefined equidistant periods of time. So every second or every half second, whatever, we are acquiring a measurement. Now let's take a look at the second group, the alternative to the step sweep. Here we call it the glide sweep. And the key characteristic of a glide sweep is that the generator frequency changes continuously. We have no longer steps as with the frequency step sweep. Here we have a continuous increase of the generator output frequency. Glide sweeps have a couple of advantages. The first one is quite obvious. As we have no longer steps, we have covered all frequencies in the corresponding band. So whatever we are interested in, we may read it out from the acquired result. Second, glide sweeps are very fast. They are much faster than step sweeps. And what is in addition, we can predict, we can define the duration of the sweep in advance. So we already know before the sweep is being transmitted how long this test will take. And a third advantage is that glide sweeps are less sensitive to standing acoustic waves. If we have to execute an acoustic measurement in a room, we always are encountering the threat that some standing waves will build up due to reflections from the walls or from the ceiling. But as we are continuously changing the output frequency, there is much lower risk that such standing waves will show up compared to a step sweep. There is also one disadvantage of glide sweeps because we cannot measure total harmonic distortion plus noise. It is possible to measure the distortion, the harmonic distortion, whatever, but we cannot measure this noise component. And we can also not measure the intermodulation distortion with the glide sweep. Now let us take one more a closer look at the comparison between a step sweep and a glide sweep. The step sweep acquires the corresponding levels, the corresponding measurement results for each step, for each frequency. So the analyzer synchronizes to each individual frequency and then measures the corresponding results, and that gives us this stepped result graph. On the other side, the glide sweep is a transmission in one run, in one shot. So we are acquiring the whole signal with the analyzer, and then the analyzer calculates the required results by comparing, this is a little bit a simplified explanation, by comparing the acquired glide sweep versus the generated one. So it is obvious that with the glide sweep analysis, the amplifier must know, it must have the information of the generated glide sweep. Then it can calculate the results. If we take a look at some individual parameters of sweeps, we can compare the two types as well. First of all, let's take a look at the resolution, the number of points of sweep. When we talk about a step sweep, we have to define this number of points in advance. It's a generator setting. And keep in mind, the more points we are transmitting, the longer takes the sweep. In a glide sweep, this is opposite. Here the analyzer decides or calculates the number of points, of result points. So here we have no relationship between the number of points, the resolution, and the duration of the sweep. If you take a look at the generator output weighting, we can see that both types are identical. We can do that with both sweep types. What does it mean? Let's take a brief look at this schematic view. Let us assume we want to measure a loudspeaker, and we want to make sure that the driving signal for that loudspeaker has an absolutely flat frequency response. But we know that our amplifier here is not perfect. It has a kind of a shaped frequency response. So by creating the inverse signal of this frequency response here, the inverse signal, we can compensate for this behavior, resulting in this flat frequency response here at the driving voltage. Another example of a generator output weighting would be a loudspeaker test where we reduce the driving level at high frequencies. This is usually done in manufacturing halls because you want to save the hearing of your staff, because high frequencies can be tested at lower level compared to the low frequencies. Another parameter would be the analysis of an externally generated sweep. That means that here the generator signal does not come from the test instrument itself, but for instance by the device under test or by some external generator which is located remote. Anyway, both sweep types can handle this application. When we take a look at the analyzer, the way how it measures, we will see a difference because the StepSweep continuously settles to the incoming signal and then executes the measurement. Whereas the GlideSweep requires a pre-adjustment of the input range. So the analyzer, the sensitivity of the analyzer must be pre-adjusted in order to avoid clipping. And last but not least, if we want to apply a weighting filter, for instance, an A weighting filter on the input signal, we can do that with both sweep types, Step and GlideSweep. Some few words about Amplitude Sweep. Just keep in mind we have already presented a webinar on amplifier testing where we are providing more information of Amplitude Sweep because Amplitude Sweeps are typically used for amplifier testing. In the Amplitude Sweep, we have an input signal with a stepwise growing signal. So the generator is stepwise increasing its output level. This is being fed through the device under test and then measured. Now, if we, for instance, measure the output level of our device under test and we know the stepwise increase of the input level, we can determine the linearity. Output level, now when we measure, versus the generated input level gives us this curve, which for an amplifier should be as straight, as linear as possible. Another alternative would be to measure the power, the output power of the device under test versus the input level. Or, as shown in this graph here, the distortion, the output signal distortion versus the input level. Time sweeps are usually used to analyze the behavior of the device under test over time. Give you some examples. For instance, if you want to determine the long-term stability of an amplifier or a loudspeaker, or if you want to analyze the response of a machine to power on, you want to measure the vibrations of this machine after it has been switched on. Or you want to measure the time response of an amplifier or a compressor to quickly changing input signals. Let me show you that in two pictures. Here we have an amplifier and an omnidirectional sound source. And here you see a recording of the output sound pressure level over time, over 1 hour. Due to the growing temperature, the higher temperature in the two devices, the output power is going to be reduced slightly over time, and this can be perfectly measured with a time sweep. Or a second example, here we have a compressor. The compressor always tries to bring the output signal into this green band as long as there is an input signal present. So here you can see here we switched on the input signal and the compressor immediately reduced the level to the point where it is within the green band. If we suddenly reduce the input level, it will start to amplify the output signal so that it is back in the green band. And here once again a sharp increase and the compressor reacting over time. So in order to analyze this behavior, we would also select the time sweep. Well, I'm at the point of my practical presentation. I have here on my desk an FX100 audio analyzer with a connected amplifier, which is my device under test, and I'm controlling the instrument with a PC under FX control. Here you see the hardware environment view of my FX100, and I just want to show you very briefly how you would virtually connect this Flexus instrument with the device under test with my amplifier. I'm connecting this one to channel 1. Now switching over to the worksheets, let me now create a glide and a StepSweep setup to compare these two methods. The first thing we do is we define the output level of our generator. So we are switching on the output and we are selecting an output voltage of 10 dB volt. Next step would be to drag and drop the generator panel of the GlideSweep to our worksheet. Now we select the 80 kilohertz bandwidth because we also want to analyze the upper harmonics. Then we would start at 50 hertz and measure up to 20 kilohertz. Here we have a parameter which is called fade in. It is apparent that when we execute a GlideSweep, we cannot start right away with the maximum voltage from the very first milliseconds. You have to a little bit fade in, slightly increase this input voltage, or sorry, the output voltage over a short amount of time. So here I'm selecting 200 milliseconds, but I'm reducing the duration of the GlideSweep itself to 1 second. And as we also need a small fade out, you can see that this gives us the overall duration of the GlideSweep, which is already defined now. Next step, we drag and drop the StepSweep generator panel to our worksheet. So here you can see I could select either frequency sweep, amplitude, time sweep, or table sweep. But I choose, of course, the frequency sweep in order to compare the results with the GlideSweep. Next point here, I select the same bandwidth, 50 Hertz to 20 kilohertz. And last point, and this is a difference to the GlideSweep, here I have to define the resolution, the number of points I'm measuring in advance, and I'm going for 100 points. So the next step in my preparation procedure is to bring the GlideSweep analyzer panel to my worksheet. And in here, I have to define the number of points I want to calculate. You see, this is the difference. Here it was in the generator, StepSweep generator, the setting, and in the GlideSweep, it is the analyzer setting. Next, I have to adjust the input range of my analyzer. This is what I mentioned before. So you can see I have a 10 dB volt output level, and I will add a little bit of a reserve, which means a headroom. 13.3 dB volt should be sufficient. That is my input range, GlideSweep input range. Last but not least, I add the StepSweep analyzer panel here just for being complete. There's no adjustment which I have to do here. Now, my next step would be to select the measurements that I want to analyze. I start again with the GlideSweep, and I should go for the level, which is the frequency response measurement. And in addition, I want to measure the total harmonic distortion of my GlideSweep transmission. And in order to be comparable, I do the same for the StepSweep level, and I can fortunately show both results, GlideSweep and StepSweep, in the same graph. And here you see now, second step, THD to the lower result graph. Now I'm already ready for the measurement. Let's do it. By the way, I have connected also a loudspeaker to my amplifier, so you will be able to listen to the sound of these two sweeps, and please notice the different time it takes to execute them. I hope you heard it. You heard that the StepSweep took much longer than the GlideSweep. And you see here the results, the green and the pink curve for the two measurements, level and distortion. And you can see the results are identical. In other words, the accuracy of both methods is identical. You're not losing any accuracy by executing, for instance, a glide sweep in a fraction of the time you would take for the step sweep. So let me come back to my presentation. Here I have provided a matrix which shall assist you in finding the best solution for your application. I just focused on the key parameters that determine which sweep type you should use. Let's start here with the measurement duration, stating if you're looking for a fast measurement, let's go for the glide sweep, because here we're talking about a very low 100 milliseconds or maybe half a second up to, let's say, maximum 3 seconds. It depends on the device and the test within which you can execute your measurement. Whereas for the step sweeps, you need more seconds. Depending on the resolution, can be even half a minute or a minute. However, if you have to determine the THD plus N or an IMD analysis, only step sweep measurements can do that. The amplifier linearity is typically acquired by means of an amplitude sweep, whereas this table sweep, this little bit exotic solution, of course, can be executed with a step sweep, and there is also a possibility to get these results from a glide sweep. Giving you just one example, let's assume you have a device that you have to test, and in the specification, it is said exactly at which frequencies it has to be tested. And let's assume that these predefined frequencies do not match the ones that would come out from a standard frequency step sweep. So in that case, you of course either could use or apply a table sweep, or in some cases you can also read out these frequencies at these predefined points from a glide sweep response. Summarizing the key information of the presentation, the glide sweep is a very fast and accurate solution. It is very versatile. You can execute a lot of measurements in a very short amount of time, and you can use it for internal analysis. Internal means the generator of your test instrument transmits the signal through the device under test, and the analyzer measures it. Or you could also analyze a sweep signal that has been generated by an external device, a remote generator, or by the device under test itself. Talking about step sweeps, the frequency sweep is an alternative to the glide sweep, but definitely slower. The amplitude sweep is mainly used for amplifier testing, measuring the linearity. The table sweep is a rather exotic, only rarely used solution. And a time sweep is a method to determine the behavior of a device under test over time. Well, I'm at the end of my presentation. Thank you very much for your attention. I hope I was able to answer most of your questions. And as stated in the beginning, we will have a follow-up webinar on advanced topic of sweep analysis in the near future. You will receive an invitation email as usual. For the time being, thank you very much for your attention. Have a good time and bye-bye.